Okay, if it happen that you don't understand anything about the definitions that I've told you or how to use this, alright, this is the purpose of me doing this video now, because I'm going to use this thing to derive a certain thing for you to understand. Alright, so this thing, let us just continue with this. Okay, so I have a certain transfer function, if you still remember, is g of s is equals to 1 over s squared. Alright, if you don't understand where this is, how does this link to the previous parts, you can just watch l10, this all things. Alright, as this is the continuation of all these three videos. Alright, so let's continue. Alright, so imagine you have a transfer function called 1 over s squared. Okay, so how do you represent in terms of a discrete system like this? Or how do you find its digital domain? Alright, or the digital transfer function. Alright, so first thing first, I'll just rewrite as this. Alright, so I'll just copy this. Alright, so this u of s, I'll just rewrite as be 1 of s over u of s. Okay, next, I can write as u of s is equals to s squared y of s. Right, it's because I bring this thing up, I bring this thing up. Alright, it's just rearranging. So what I will have is u of s is equals to this thing. Alright, next, our inverse Laplace. Inverse Laplace of u of s, you would have u of t. Inverse Laplace of s squared of s, you will have y prime prime, alright, of t. That's all, because it's s squared tell you that you are differentiation of second order. That's all it is. Okay, and then this is t lah. Okay, time. Alright, next is that I'll rewrite things, and take note this part is a standard part. Alright, although this is a very simple thing, alright, but you also need to remember that whenever you see a state space, you just write y as equals to x1. That's it. Alright, this is the very key important thing that you need to write, y equals to x1, standard. Alright, so if you differentiate x1, for example, alright, if x1 dot, alright, you have what? What do you have? You have called x2. Alright, so I can rewrite as y dot is equals to x1 dot is equals to x2. Alright, so next, I'll just write y double dot, alright, as equals to, since we know that y dot is equals to x2, so y double dot is x2 differentiation. Alright, I'll have what equals to u, because u is equals to y double dot, right? So this is that y double dot is equals to x2 differentiation equals to u. Alright, you can take a little few, I give you about 2 seconds, 3 seconds, just compare with this. Alright, just take a look. Alright, I'm actually rewriting this as this one. Okay, so at first you need to just write y equals to x1. If you have a differentiation second order, you just differentiate and differentiate, representing x1 and x2 all together. Okay, so in other words, you're actually dissecting your second order into two first order system. Alright, the first order is x dot 1, or this is x1, this is x2. Alright, so this is x dot 1 and x dot 2, you see. So it's just two first order. This is first order, this is also first order. So the purpose of the state space is often rewriting everything in terms of a first order. So this is the first order, this is also a first order. Okay, let's remember this step, y equals to x1, and then you own self go and differentiate, happy you are. Alright, next thing you need to understand, to write, is to write in terms of x dot 1 and x dot 2. Okay, this is something that you often they give it to you, but you don't even know how to write that. So whenever you see x1 and x2, you know that x dot 1, x dot 2 will be definitely at the front part over here. Is equals to some matrix, alright, and then x1 and x2, and then plus, alright, a certain matrix u. Okay, and then over here you'll just write as y as equals to some matrix, alright, x1 and x2 plus du. Alright, often du, never mind, just read it first. Okay, so you need to know how to write in terms of this form. Alright, although this always comes to you, but you also need to remember how to write this, because in exam I don't think they will tell you how to write this. They will not give you anything about here. Alright, so you need to own self write this x1 and x2 over here, and your x dot 1 and x dot 2 over here. Okay, so this thing over here is your this thing, while this thing over here is your this thing. Okay, So I can say that this is my F, this is my G, this is my H, this is my J. Same thing. Alright? So I'll just simply submit this information into this state space. Alright? So Y is equals to X1. Correct? So Y is equals to X1. So 1 times X1 is equals to Y. So 0. So Y is equals to X1 only. It doesn't have any like plus U. Don't have, right? Or plus 3U. Don't have anything like that, right? So therefore this thing over here is just simply 0. Because there's nothing about in terms of U. Alright, if I have like Y is equals to X1 plus 3U, then I'll just write as 3 times U, something like that, or 3U lah. Okay, but because we don't have, so I'll just ignore that. Okay, so this is just 0. Okay, this is the first step you're gonna write. Next, alright, the x1 dot is equals to x2. So the x1 dot is equals to x2. Right, so 0 times x1 is 0 plus 1 times x2 is equals to x1 dot. Alright, it's same thing. X1 dot is equals to x2 lah. Alright, plus 0u. Right, there's no u, right? So I'll just write as plus 0u. Next, alright, your x2 dot, is equals to your your x2 dot is equals to u. Alright, so it's not equals to x1 or x2. Is by itself, x dot 2 is equals to u straight away. So over here is just simply 0 and 0. Okay, because there's no x1 and x2 in terms of itself, right? X dot 2 is equals to u straight away. Alright, so it's equals to u, since therefore it's just 1 times u. Okay, so therefore you have your state space all along already. Alright, and take note, this is still in the analog domain. Alright, these are all in terms of the transfer function, s squared, 1 over s squared. Alright, so what I've been doing is all in terms of a analog transfer function still, your state or analog state space. And this thing over here is very similar to what you have seen in the previous earlier part. This thing ax plus bu, we can also write as ax plus bu also. So over here in this section, alright, if you want to leave it as a answer for your analog system, you can just write as A, you can just write as B, you can just write as C. Alright, but if you want to use it for your discretized system, then you will change the name as F, G, H. Alright, where if you have a D, then if it's I, something like that. Alright, or in other words, you have some du. Alright, so in this case, instead of D, I'll just write as I. It's the same not I lah, I should say J, but anyway, it's F, G, H, J. Okay, so in the discretized domain, you just write everything in terms of F, G, and H. Alright, so this matrix of vectors all over here are all your so-called the analog system still. Alright, so therefore what we have done so far is only doing this thing. Alright, I haven't discretized it yet. Alright, so therefore I think I'll just leave you to this part. Alright, at the analog state space, okay, which is this one over here. It's because I just want to make things very packed within this video. So I'll just carry on with the next video on transforming this thing into this thing over here. Okay, eventually we'll get this thing over here. Alright, so in the next video we'll talk about how to get this, because this thing over here is also a quite heavy stuff. Alright, so I'll just see you in the next video to discuss on that. So see you there.